Not visible light coming from the plasma. The plasma is this sort of 100,000 degrees temperature, but what you actually see is the coldest part. The hottest part, you really don't see it because it's too hot to emit light in the visible, isn't it?
Yes.
When I started, I was doing numerical modeling, and then I realized that running the machine was a lot more interesting and a lot more fun for me. My work is stressful. My work can be very demanding in terms of time, but this is still one of the most exciting places in the world.
Here in Oxford, you'll find arguably the most successful fusion experiment on Earth, JET, the Joint European Torus. Torus being the technical term for donut, which is how the reactor's shaped.
JET's been operating since the early 80s, and only by 1997 were we really ready to try proper fusion. And we produced 16 megawatts of fusion power at the time, which is like a few wind turbines. It's pretty significant, and it shows that fusion is possible.
The 1997 experiment set records, but the reactor was only able to run for less than a second. The team spent the next 2 decades cooking up a new approach, and in 2021, they gave it another shot.
We always knew that we could do better. The last 2 days before Christmas were dedicated to these experiments, just this window of parameters where we could get more. And we did.
3, 2, 1.
JET more than doubled its previous record, producing more energy than any fusion experiment in history.
We couldn't hug, we couldn't high five, nothing, because we have to be at 2 meters from each other. But, you know, it was obvious that this was a record. It was successful. You could see that it was successful.
It's a real step towards the ultimate promise of fusion, a cheap, emissions-free power source with virtually unlimited fuel. But maybe don't break out the champagne just yet.
So in the 1997 experiments, we produced a lot of power, but very transiently. So it ramped up and then we lost control. Now we ramp up and sustain for 5 seconds.
So what exactly makes fusion such a tough problem that sustaining it for 5 seconds constitutes a world record?
Nuclear fusion. Once it's perfected, fusion power will give us an unlimited supply of energy.
So nuclear fusion is really what is happening inside the sun, where lots and lots of hydrogen atoms are moving at immense speeds. And every so often, some of them fuse together to form helium. Now, the process at the atomic level leads to a very small amount of loss in mass. And that little amount of mass actually generates a lot of energy. And you do that millions and millions of times, and you get the sun.
Well, look, we know fusion works. It's happening right now in our sun. But the reason it's happening in the sun is because of the mass of the sun. It's so massive, has this huge gravitational force, which is pushing those isotopes of hydrogen close enough to fuse. We obviously cannot recreate the mass of the sun here on Earth. So instead, we have to give that fuel even more energy. So we take a gas, we put a huge amount of energy into it, and that turns it into the 4th state of matter, of plasma.
If you consider water, for example, it's ice, then you warm it up, and then you get a fluid, and then you warm further up, you get a steam, and if you then increase temperature even further, then you get plasma.
Common plasmas include lightning, neon lights, and these things.
We need temperatures 10 times larger than in the solar interior. So this is about 100, 200 million degrees.
And only at those sort of temperatures do you get fusion to happen here on Earth.
Heating something to 10 times the temperature of the sun is, to use the technical term, very hard. Scientists have been working at it since the 1930s.
The major breakthrough has been the first tokamak experiments in the 1960s in the former Soviet Union. They achieved several million degrees, and this was a real breakthrough.
Tokamaks are still one of the most popular ways to create fusion. That's what JET is, along with many other government-run reactors around the world. Using powerful magnets to contain the plasma, they've achieved temperatures of 100 million degrees and well beyond. But there's still one big milestone we need to reach before fusion power becomes a reality: net gain.
We need more power out than put in to heat the fuel in the first place.
If we can't generate more power from fusion than we put in, then the whole thing's a bust. Unfortunately, no one's ever done it, not even the brilliant minds at JET. That's all kinda part of the plan though, because JET isn't actually designed to solve fusion all by itself. It's just set up for a much bigger project called ITER. ITER.
We are building this experimental machine in the south of France, ITER, which is going to be big, and it's the first one that will produce really more energy than what it consumes.
ITER is a massive international collaboration between 35 different countries, and everyone involved seems pretty confident it's going to get to net gain for the first time. So, fusion's just around the corner, right? Well...
With the ITER project, the first plasma is supposed to be created by 2025, but full fusion reaction isn't expected until 2035. So if ITER were the only bet that we were making on fusion, then it would be a safe bet to say that nuclear fusion is going to take decades. And that's too long for the climate fight.
Even the most optimistic scientists think that fusion power may not be developed for 50 years, if then, if ever.
Some think we can get there much faster, away from the traditional tokamak design. If you have followed fusion at all in recent years, you might have come across this steampunk octopus, an earlier prototype of their reactor.
It's very analogous to a fusion version of a diesel engine. So you have this very large cavity that's opened up inside of liquid metal. And into that liquid metal, we inject a high temperature plasma of hydrogen. We can now perform this compression to heat up that plasma very much the same way you think about a piston compressing and heating the fuel in a diesel engine. This is a steam-driven compression process using an array of drivers. It compresses and heats this magnetized plasma to fusion conditions.
General Fusion's reactor would create brief bursts of fusion energy, an approach they hope will achieve net gain more easily than a tokamak. Founded in 2002 and supported by investors like Jeff Bezos, they're one of the furthest along in the field of fusion startups, with plans to build a demonstrator plant by 2026 in Oxford on the same scientific campus as JET.
This thing won't actually put megawatts on the grid, but it will prove that our approach to fusion in a power plant relevant environment can actually make fusion happen. Private fusion industry. Of course, I came to General Fusion because I like General Fusion's technology. That's one man's opinion. I think we have, my view is the first really good shot on goal, but what really feels good is there's going to be lots of shots on goal, right? And I'm very confident we're going to score the win that we need.